Today we will be talking of hidden surface removal. In the last class I had introduced this topic. Today we will see a set of algorithms which can be used for removing hidden lines. We will see two types of algorithms. One type of algorithm consists of those algorithms which operate in what are called the device coordinates or the image coordinates, or they operate in image space. Okay, the other operates in what is called as object space. Okay, typically when you are talking of the object space, we are talking of the world coordinate system where the space is infinite in all the three directions. Okay, this is the world coordinate system. If an algorithm is operating in image space, we mean that we are talking of the screen coordinates. A portion of this world coordinates has already been transformed onto the screen. Okay, we already know that a finite portion of this world coordinates is going to be mapped onto the screen. Okay, and then the hidden surface removal algorithm will operate on this transformed image. Okay, these are two different types of algorithms.
Suppose you have defined a polygon in the world coordinate system, which is large enough.
Yeah.
And you want to transform in the screen.
Yeah.
So you want the whole polygon to be transformed, or the few portion of it.
See, if we have an object in this world coordinates like this, okay, since we are talking about three-dimensional space, this object will be clipped according to the volume that is going to be displayed. Okay. Let us say we are looking at the world coordinate system from this point in a perspective transformation, in a perspective view. Okay. Our view is somewhat like this, and we define that on this projecting plane only a finite portion of it we are going to see. Okay, which means that if we take rays starting from here, these are rays like this, if you look at this pyramidal structure, only whatever is inside this pyramid that will be visible, whatever is outside this pyramid will not be visible. Is that alright? Okay. So this coordinate system is my world coordinate system. So let us say this is x, y, and this is z direction. Now in the world coordinate system I have defined a finite volume, or I have defined a finite portion on my projecting plane. Whatever lies inside this projecting plane will be visible. Okay, that will correspond to a pyramidal volume. Okay, so an algorithm which is operating on the object space will first look at the object in the world coordinates. It will clip it in three dimensions such that only portions inside this pyramid are visible.
So we are going to choose our own plane and our own viewing point.
All that will be specified. This projecting plane, position of the eye in the case of the perspective projection, or the direction in the case of parallel projection, all that will be specified. Once we know the viewing direction, once we know the projecting plane, only then we can talk of removing hidden lines. Okay. For example, if you have any object, okay, if you have a block, if you look at it from this direction or you look at it from the other direction, in both the cases the portion that will be hidden will be different. Is that alright? That is why whenever we are talking of hidden surface removal, whether we are talking of the world coordinates or the screen coordinates, we are always talking of with respect to a specified viewing direction. Okay. If we have an object like this, If I am looking at it from a direction from which is from that side, then the set of planes which will be visible will be totally different. Okay. So, if I have my world coordinate system, whenever I am trying to remove hidden surfaces or hidden lines, I have to specify my viewing transformation. Okay, so the viewing transformation we have already seen that can either correspond to a perspective view or it can correspond to a parallel view. Okay, whichever view we take, the viewing transformation has to be specified. Okay, once this viewing transformation is known, then we will talk about hidden surface removal. Okay, an algorithm which operates in object space will look at all the objects in the world coordinate system. Okay, in the world coordinate system, our space is infinite in all directions. Okay, it will extend from plus infinity to minus infinity in x direction and in the other direction as well. Okay, it will look at all the objects and then decide which objects are closer to the eye. Okay, while when we are talking of an algorithm working in screen coordinates, it will take a finite plane, a finite portion of it, a finite portion on the projecting plane, get a three-dimensional pyramid, okay, and it will only look at objects which are inside this pyramid. Okay, so an algorithm which is operating in object space this will do hidden surface removal for all objects. Okay, while an algorithm operating in image space okay, it will take the objects and these objects will undergo a process of 3D clipping. Okay, 3D clipping means only objects inside this clipping volume will be displayed. This pyramidal structure or this pyramidal volume in the case of perspective view is called the clipping volume. Okay, only objects inside this clipping volume will be considered. Okay, and those objects will be transformed to the screen coordinate system. Okay, the screen coordinate system is this coordinate system. Okay, that means if the resolution of the screen is 1024 cross 1024, all these objects will be defined between coordinates from 0 to 1024. Okay, plus there will be some z value. Okay, so when an algorithm operates in image space, the objects first undergo 3D clipping, then they are transformed to screen coordinates. Okay, and then we decide which objects are closer, which lines are closer and which lines are at the back. Okay, so hidden surface removal in image space is carried out after 3D clipping, after transforming all the points to screen coordinates. Okay, while when you are operating in object space, hidden surface removal is carried out for all the objects. Okay, and then we will carry out a process of clipping which will be in 2 dimensions now. Okay, because we have an infinite world. From the infinite world we have taken a projecting plane and decided which objects are closer. Okay, we have transformed everything onto the projecting plane now. Okay, so now the operation of clipping that will be involved will only be a 2-dimensional clipping. Okay, so in this case only 2D clipping will be involved, and in this case we carry out 3D clipping and then hidden surface removal. Okay, so I have two different types of algorithms in these two cases. One thing you should keep in mind in the case of 3D clipping, right now I have shown a pyramidal clipping volume. Okay, it need not be a pyramidal clipping volume. If you are talking of a parallel projection, then the clipping volume will be a block. Okay, that will look like this. This is a projecting plane and we define a window on it like this. My clipping volume would look like this. It will be a block kind of clipping volume. Okay, and typically when we define a clipping volume like this, we also define a front plane and a back plane. We will say all objects behind that back plane will also be clipped off. Okay, so the clipping volume in this case would look like this.
What's the need for this backplane?
The need for the back plane, it's just that in some cases you might like to say that all objects behind a certain plane are not to be considered. It's just that, nothing beyond that. Okay, we need not have it. There will be back plane and a front plane. Okay, all objects in front of a plane, that also we might like to clip them out. Okay, so we normally define a clipping volume which will consist of 6 planes like this. In the case of perspective, also we will have the same 6 planes, but they will form a frustum of a pyramid. Okay, there will be front plane and there will be a back plane. Okay, now let's look at some clipping algorithms. The first algorithm that we will consider is what is referred to as the Z-buffer algorithm. Okay. Now this Z-buffer algorithm, it uses what is an extension of a frame buffer. You remember what is a frame buffer? What is a frame buffer? Anyone?
It stores the information which is read by the controller. No.
What information does it store?
Different entities.
Different entities? No.
The information required to draw any figure on the screen and say in line vector.
Coordinate frames of that.
Coordinate frame? No. They've forgotten everything.
The endpoints basically. Say,
No.
So, pixel is on, which pixel is off, basically.
it's a set
Which
of
pixel is off and which pixel is on?
on, yeah.
A
Zero.
frame buffer stores information about each and every pixel. Okay, so if you have a screen like this, okay, this is from 0 0 to xy. This is an array of pixels which is x times y. For each pixel, we have a bit which describes whether that pixel is going to be on or off. If it is 1, it is on. If it is 0, it is off. That is in the case of a monochrome display. In the case of a color display, we will have multiple planes. Okay, so this is what is a frame buffer. Now, when we are talking of a Z buffer or a Z buffer, the same formula, the same concept is extended, and instead of a bit, at each pixel we will store the depth of the pixel also. Okay, that means, let us say if we have a plane which is being displayed like this, at this pixel, let us say the depth of the entity that is being displayed is 100 units. at some other pixel the depth might be different. Let's say at this pixel the depth is 200 units. Okay, so we'll also maintain a Z buffer which will store the depth of the pixel being displayed at each pixel. Okay, so the resolution is x times y. We'll use a frame buffer which will be of the size of x times y.
So it stores information even for the pixels which are off.
For the pixels which are off, the depth that is being displayed will be some default value at infinity. Okay, the minimum z value that we have, that will be stored initially for all the pixels. Then what we will do is, let's say this is one polygon that we have to display, and we have another polygon to be displayed like this. Okay, this is polygon number 1, this is polygon number 2. Now for the polygon number 1, when we came at this pixel, we decided that it had a depth of 200. Then when we are looking at polygon number 2, and again we are trying to display the same pixel, let's say the depth of this pixel is equal to 150. Okay, this value 200 is available in the Z buffer. Okay, so while displaying polygon number 2, we'll compare the depth of this pixel, that is 150, with the depth which is available in the Z buffer.
Where do you store 150?
See, 150 is the depth of this polygon. We are trying to display this polygon. Okay, when I am trying to display this polygon, I know the equations. I know the equation of the plane. Okay, so I can calculate the depth at each and every point.
And this value will then be transferred in the Z buffer.
Okay, now I will compare this 150 with the value which is stored in the Z buffer and decide which pixel is closer to the eye. Okay, 150 is closer to the eye, so I will change this to 150 and I will decide that at this point pixel number 2 is to be displayed. Okay, so we will use an array of the size of x times y. Okay, x and y are the resolution of the screen in the x and the y directions. In the x direction the resolution is x, in the y direction the resolution is y. So we will use a buffer or memory space which will be of the size of x times y. And it again,
Are you storing information regarding which polygon it is?
yeah, which polygon and the display information with respect to that will go into the frame buffer.
This pointer will also go.
Yeah,
Polygon.
that information will also go. Okay, because if I am displaying polygon number 1, let's say that is of a different color, okay, or it has a different intensity, that information will be stored in the frame buffer. Okay, the moment I update it by the information of a second polygon, the display characteristics of the second polygon will be put into the frame buffer. Okay, so let's just see this the steps involved in this algorithm.
So does the
Yeah.
Z buffer contain the depths of the nearest point?
The nearest point that is currently being displayed at that particular pixel. 1 minute. See,
No, for all the points it doesn't compare and store the nearest point.
what do you mean all the points? Comparing this point with this point?
No, comparing this point with the same point which would then be there in other.
Yeah, so it will compare the depth at this pixel for polygon number 1 with the depth at this pixel for polygon number 2. Okay, so at this pixel it will compare the depth of each of the polygons, and whichever is the closest to the eye, that will be displayed. Yeah, you're saying something?
Suppose the first polygon is a rectangle.
Yeah,
Then every pixel which is off outside the rectangle will have the value infinity,
yeah.
and inside the pixels which are off inside the rectangle, what values they will have?
See, this is your screen, okay, and you have this rectangle to be displayed. Okay, when you are displaying this rectangle, all the pixels inside this, they will take a z value which will correspond to the depth of the polygon of the rectangle at that position.
The rectangle is a 2D.
No, when I am talking of a polygon, I am talking of a planar surface. Okay, I am not just talking of a single polygon. We are talking of planar surfaces. Okay, if you are only talking of a wireframe kind of situation, then hidden surface removal is not relevant. Okay, in a wireframe kind of situation, even if I have a rectangle behind it, even that has to be displayed. Okay, whenever I am talking of polygons, I am talking of planar surfaces bounded by these polygons. Okay, so all points which are inside this rectangle, the z buffer for those pixels will take a value corresponding to the depth of that polygon, depth of that rectangle. Okay.
So in the z buffer, we are finally storing for the intersection between polygons only the nearest points, the depth of the nearest point.
So what will happen is, for this portion, the depth of the first rectangle will be shown. For this portion, the depth of the second rectangle will be shown, and for this portion, the nearer of the two will be shown. But they can be intersecting. Okay, so if they are intersecting, in that case, for a part of it, one polygon will be shown. For the other part of it, a second polygon will be shown. Okay, they can have an intersection which is something like this, because we are talking in 3 dimensions. Okay. Okay, so let's see the different steps involved in the algorithm. Okay, what are we given? We are given a set of polygons in, are we working in image space or in object space? I have described the algorithm. Are we working in image space or in object space?
Image space.
We are working in image space in this case. Okay, so we are given a set of polygons in image space. Okay, and what do we have to do? We have to remove the hidden surfaces and display all the polygons. Okay, and what is the algo involved? The first step is set the frame buffer and the z buffer to a background value. Okay, a background value, in the case of a frame buffer, it will have some background intensity or background color. Okay, what that basically means is that initially we will set the whole screen to correspond to as if nothing is being displayed. Okay, that means whatever is the color of the background, whatever is the depth of the background, that will be initialized to all the pixels. Okay, that is the first step. Okay, this means that the z buffer will be put equal to some minimum value. Okay, and the frame buffer will go to the color and intensity of the background. Okay. Then what we have to do is, for each polygon to be displayed, we have to decide the color, intensity as well as the depth of each pixel. Okay. Like in this case, we first have to decide for this polygon what is the color, intensity and depth at each pixel. How do we do that? What algorithm do we use? Polygon filling, okay, or scan conversion. Okay, so we'll use a scan conversion algorithm. Just scan convert each polygon. Again, while scan converting, we'll say for each pixel find the depth at that point. Okay, and if z of xy is greater than the z buffer, okay, z of xy is greater than the z buffer. Right now what I have done is the z buffer I have initialized to a minimum value. Okay, that means the point which is the farthest from the I am taking that to have a negative z value. Okay, so z of xy is greater than z buffer. In that case, we will update z buffer, okay, and we will update the frame buffer. Okay, z buffer at xy, yeah,
Updation is frame buffer for any change in color.
yeah, for any change in color intensity. Okay, so z buffer at xy will be equal to z of xy, and the frame buffer will be updated according to the color and the intensity of that polygon. Okay, so both z buffer and frame buffer for that polygon will be updated if z of xy is greater than z buffer of xy. Okay, and this process will repeat one by one for every polygon. When we complete this whole process for all the polygons, then we would have decided for each pixel. Okay, if we have a set of polygons like this, okay, if we have a set of polygons to be displayed like this, at the end of the algorithm we have decided for each pixel what is the depth of the polygon being displayed and what are the color and the intensity being displayed at that point. Effectively that means that each pixel would have decided which polygon is being displayed. Okay, so this way by scan converting each polygon one by one and maintaining a z buffer, we are able to remove the hidden lines and display only those polygons which are closer to the eye. Okay, this algorithm is called the z buffer algorithm. Now from this algorithm it should be obvious that we have to scan convert each polygon. Okay, that means if we have a number of polygons, for each pixel we will have to decide the z value and compare. Okay, and the amount of space that we are going to use is going to be x times y. Okay, x times y. If you have a screen which has the resolution of this, we need space which corresponds to roughly about 10 to the power 6 integers. Okay, which is 10 to the power 6 into 4, which is equal to 4 megabytes. Okay, that much of space would be required to maintain the z buffer. Okay, so in this algorithm the space involved is very large. Okay, the space involved is proportional to x times y. Okay, the space involved is very large and is typically of the order of a few megabytes. Okay, especially with high resolution screens. Okay, and we have to scan convert every polygon, so it is expensive in terms of time.
So what is the normal resolution of the screen of workstation?
Of that order.
This order. The silicon graphics?
In fact, even the VGA monitors, PCUs that you have screen of this order these days. the older ones, the CGA earlier one, they used to have resolution of 640 cross 256
320.
or 640 cross 320, those kinds of resolutions. Okay, but now this resolution of screen is quite common.
It's a bit higher for Sleevin graphics.
Yeah, it's a bit higher, only 1324 or something. Yeah. Okay, so this algorithm takes a lot of space, plus it is also expensive. Okay, because scan conversion has to be done for each and every polygon one by one. Okay, any question about this algorithm, the Z buffer? Okay, then we'll go on to the next algorithm, which is a slight modification of this algorithm. This is called the scanline Z buffer algorithm. Okay. See, if you notice in the Z buffer algorithm, this is the screen, and if I have a polygon like this, I am going to scan convert this polygon, and scan conversion involves scanning it row by row. Okay, so I first scan this polygon row by row, then I am taking the next polygon which looks like this, and now I will start scanning this algorithm row by row. Sorry, this polygon I will start scanning that row by row. Okay, and as I am scanning, the display coordinates, the display characteristics of each pixel I am going to store in the Z buffer as well as the frame buffer. Okay, instead of that, what we will now do is first look at one row, look at all the polygons which are inside that row, which are crossing that row. Okay, and decide for this row which are the polygon display. Okay, so I will do my scanning. Okay, but I will do it row by row, okay, or a scan line by scan line, and for each scan line I will first complete all the polygons. Okay, so essentially for each scan line, okay, I will convert or I will scan convert all polygons. Okay, if I take one scan line, I complete all the polygons for that, then I take the next scan line and I complete all the polygons for that. Then what I can do is I will maintain a scan buffer which will be, the size of that will be equal to the resolution in the x direction. Okay, the resolution in this direction is 1024. Okay, I will maintain an array of size 1024. Using that array, I will scan convert the first row and display all the polygons that are crossing that. Then I will use the same array and use that for the second row. So once I have decided which polygons to be displayed for the first row, I don't need the Z buffer for that anymore. Okay, so now I will use a Z buffer whose size will only be 1024. Okay, earlier I was using a Z buffer whose size was 1024 times 1024. Okay, or its size was x times y. Okay, now I use a Z buffer whose size is only x. Okay, using this Z buffer, I'll first scan convert the first row, then the next row, and then the next, and so on. Okay, that is, this is referred to as scanline Z buffer. It's a similar algorithm, except for the fact that the scanning will be done scanline by scanline. Okay, and I'll maintain a Z buffer only for one row. I won't maintain a Z buffer for the complete screen. Okay, this way I'll be able to cut down on the space requirements. Okay, the space requirements will be much smaller.
At each scan line you update the previous.
Again?
At each scan line you update the buffer.
Yeah, at each scan line I'll update the buffer.
So where you transferring the information, the previous information, where are you storing that?
The previous information,
Yeah.
you mean?
I mean, side by side you are displaying the.
Being overlapped.
Yeah, see, I first look at, let's say I'm looking at this scan line. For this scan line, let's say I decide that in this portion, first polygon is to be displayed, in this portion the second polygon is to be displayed. Okay. Once I decided that, now I'm going on to the next scan line. When I go to this next scan line, I don't need to maintain a Z buffer for this, because there I've already decided that here which are the pixels, which polygon is to be displayed, and here which polygon is to be displayed. That information will be stored in the frame buffer.
Side by side you are transferring the information to frame buffer.
Yeah, the display information is always being stored in the frame buffer. Okay, if you look at the previous algorithm, okay, the moment I decide which polygon is to be displayed, I am updating the frame buffer for the display information. The Z buffer will only store the depth. Okay, so the moment I have decided that in this particular line, in this scan line, which polygons are to be displayed, I don't need the Z buffer for this line anymore. I only need the frame buffer. The frame buffer is available to me anywhere. Okay, so the Z buffer for this, I'll update that to get the Z buffer for this. Okay, I'll use the same array, I'll change its value so that it will now show the Z buffer for this scan line. Okay, so let's see this algorithm in detail. What we'll do is, in this we'll use the Z buffer for only one line. Okay, or only for one row of pixels. Okay, and then during scan conversion, you remember something called an active edge list. Okay, when you are scan converting, you are maintaining an active edge list. Now, in the active edge list, we will also try and calculate z of xy. Okay, how are we maintaining an active edge list? This is the screen. This is a polygon to be displayed. Then the active edge list at a particular line or at a particular scan line will contain the set of edges which are active. Okay, that means let's say this is the edge number 1 and this is edge number 2. Okay, so now we'll use this active edge list to calculate the z value at every point. How do we do that? Between these two edges we'll have only one polygon. Okay, so for this polygon we want to find out the z value at each pixel. Let's say the z value here is z1 and the z value here is z2. If the z value here is z1, then as we move in the x direction, okay, from one pixel to the next, the z value will change by a constant amount. Okay, since we are talking of planar surfaces, as we move from this pixel to the next or from this to this, the change in z value will be constant. Okay, so if we know the z value at the edge, then the z value after that for the next pixel can always be calculated just by saying z will be equal to z plus some delta z. Okay, z will be equal to z1 plus delta z. The next pixel will again be the z value for that will be altered by a magnitude of delta z. Okay, where this delta z can be computed according to the slope of the plane. Okay, so if you know the z value here and we know the equation of this plane, then as we move in the x direction we can compute the z value at each and every. Okay, and as we compute the z value, as we compute z of xy, we will compare z of xy with z buffer at x. Okay, in the previous algorithm we had z buffer of x comma y. Now we will have only z buffer of x. Okay, we will compare these two. Okay, and if z of xy is greater than this, okay, then we will update both the z buffer as well as the frame buffer. Okay, and this process will be completed for all the polygons at this scan line.
Does it mean that at each scan line the computer searches as many number of times and the number of polygons are there? Or at each point it is seeing how many polygons are intersecting and accordingly gives just one value?
No. What we'll, I was going to come to that, what we'll do is, see, we have one polygon like this and we have, let's say, another polygon which is somewhat like this. Okay, this polygon is starting at this scan line and is ending at this scan line. This polygon is starting at this scan line and ending at this. Okay, so earlier if you remember, we are maintaining a list as to where our edges are starting. Okay, we are maintaining an active edge list. In addition to that, we will now also maintain an active polygon list. Okay, so this polygon is going to start at this scan line. Okay, so we will maintain an active polygon list. As we go from one scan line to the next, we will keep maintaining what are the polygons which are added, which are getting added to the active polygon list. Okay, so we will have an active polygon list which will contain the list of polygons intersecting a particular scan line.
So what is the need? Active edge list is enough.
No.
Coloration, intensity and reduction.
For every polygon will have a different color, different intensity. Okay, and we'll first for this scan line, let's say if you just maintain an active polygon list, we might have a situation like this. Okay, we have one polygon like this and another polygon like this. Okay, you are looking at a scan line like this. This is intersection 1, 2, 3, 4, 5 and 6. Now 1 and 2 correspond to one polygon, 3 and 4 they do not correspond to the same polygon. Okay, 3 and 5 will correspond to the same polygon and 4 and 6 will correspond to the same polygon. Okay, so we will have to be very careful in taking care of this information.
So that's not helped by active polygon list.
No, we have to know as to which are the polygons which are active on this particular line. Okay, we have one polygon and a second polygon.
All of them are active.
So both of them are active. So we will first take up one active polygon, do a scan conversion for that, then take a second active polygon, do the scan conversion for that at that particular scan line. You get that?
You're doing it in 2 steps. You were supposed to do it in 1, isn't it?
We will do it as many times as the number of polygons in the active polygon list. Okay, or we can maintain a common active edge list and with each edge also keep track of which polygon it corresponds to. Okay, we can combine the active edge list and the active polygon list. That is the material. Okay, but if we have a set of polygons, then for each polygon you can have a separate active edge list and do a scan conversion at that particular scan line.
That means that each scan line it will go as many number of times as the number of polygons at each scan line.
At each scan line,
Say there are n active polygons,
yeah,
so it will go n
It will
times,
go n times.
and n times it will update.
n times it will update. Okay, but it will update only in the portions which are intersecting.
Can't this be done at one go only? Can't the objective be achieved at one go only?
See, whether you do it n time or whether you do it once, what you have to do is, for each of these segments which are to be displayed, you have to look at each and every pixel and decide the z value. That you have to do anyway. So whether you do it once or whether you do it n times is going to be the same amount of effort. Okay, because if let's say in this case, if I do it once, from 1 to 2 I will decide the z values, then from 3 to 5 I will decide the z values, okay, and then from 4 to
See, if we have the right hand polygon over coming in front to the back one, so we will store from 3 to 4 for the previous one and then 4 to 5 for the front one.
there can be an intersection between 4 and 5.
Few substance coming in between this way.
No, there is a polygon like this and a polygon intersecting it like this. 4 is the edge of this polygon and 5 is the edge of this polygon. Okay, but the two polygons can be intersecting like this. Okay,
It has to be done separate.
okay, so we will take care of that in the next algorithm. But for the timing, what we will do is, when we are scan converting, we will go from 1 to 2, from 3 to 5 and from 4 to 6. Okay, if I am maintaining an active polygon list and I first take up the first polygon, I will scan convert from 1 to 2 and from 3 to 5. Then I will take up the next polygon and scan convert from 4 to 6. Okay, whether I do it in 2 steps or in 1, is the same amount of effort. Okay, so typically we can maintain an active polygon list and then for each polygon we will have an active edge list which will help us scan convert at that scan line. And then when we move from one scan line to the next scan line, we will have to update the active polygon list, we will have to update the active edge list and we will have to update the z values. Okay. From this point we will see in the next class, we will complete this algorithm and then see how to make this algorithm even more efficient. Okay, we will stop here now.